while back, I programmed this animation. I think it's pretty neat, but the thing that really makes it beautiful is its simplicity and the mathematics behind it. Take a look at the code. It's only 10 lines. In fact, most of this is just for formatting and style, or updating variables in animation. The for loop iterates through all values of I, so the line is drawn for all values 0 through 360, and we're left with this line function, which takes in an x and y coordinate for each point. These constants are just for scaling or centering the animation and are not needed. This is much simpler now, and it describes the whole animation, but it still may be a bit vague. Let's take a look at the simplest case, the cardioid, when p equals 2. Cosine and sine essentially just get the x and y coordinates of the circle, so instead of thinking about them as x and y, we can think about them as an angle, theta. Now let's see what happens viewing the lines one at a time. It doesn't reveal much, but now let's try tracing the midpoint. It's a lemicon, close to what we wanted, but not quite. Let's try a different point on the line. If you recall, one point on the line is moving at twice the speed of the other, so let's try tracing a point twice as close to one endpoint. And we have our cardioid. If you increase p, and with it change the ratio between the traced point and the line's endpoints, the number of petals increases with it too. And, because the trace point gets closer and closer to the endpoint, the petals become smaller and smaller. These are all examples of epicycloids. You may already know that a cycloid is generated from tracing the point of a rolling circle. But how is an epicycloid defined? An epicycloid is generated in quite a similar way, except it is created by one circle rotating around another circle. Much like our line, the ratio of one circle to the other circle determines the amount of petals or cusps that the epicycloid will have. To show that this is the same as our curve stitching, we can use a parametric. This is the parametric for a circle, or a point tracing a circle. Now, let's ignore our ratios for just a second and take the midpoint of the 2 points that are generating a line, one moving p times as fast as the other. It's the lemicon again, what we expected. Now, we can multiply one of the points by p, and divide by one more than that to get our epicycloid. And now, we have a generalizable parametric representation of an epicycloid, derived from our curve stitching. Let's see if we can get the same equation thinking about it in terms of our rolling circle. We know the radius of the inner circle is 1, and we want the radius of the outer circle to decrease as p increases, so we can write this as 1 plus 1 over p. So, now we know the radii of both circles, and their combined radius equals the midpoint of the second circle. And, because we want the circles to be the same size when p equals 2, we have to subtract 1. Circumference scales linearly with radius. So, because our second circle's circumference decreases by a factor of p, its circumference will as well, causing the point we're looking for to rotate p times as fast. Adding this to the midpoint gives us the point we're looking for. Anything divided by itself is 1, so we can rewrite our equation, and then combine the fractions, cancel out the 1s, and factor out the reciprocal of p minus 1 to leave us with this equation, which does generate an epicycloid. The only difference between this and the other equation that we found is that we are subtracting 1 instead of adding 1. This causes the epicycloid to be on the outside instead of the inside of the circle. Regardless, they are both epicycloids, and overlaying one on top of the other would show that they have exactly the same shape. But something interesting happens if we make p a negative integer. Let's see how our parametric handles it, graphed on Desmos. When p equals 2, we reach the cardioid, and as it reaches 1, it approaches a singularity because we are dividing by 0. Now we are seeing these other weird shapes that almost seem to be the opposite of what we saw before. Actually, if we think about this in terms of a rotating circle analogy, it makes sense. Negative radius would mean that the circle is rotating on the inside of the larger circle. These shapes are known as hypocycloids, and will be important later. But the cardioid appears again in a seemingly unrelated area of math, the Mandelbrot set. The Mandelbrot set is created by taking some complex number c and continuously iterating it back into the equation z squared plus c with a starting z value of 0. As the iterations go off towards infinity, any number which stays below 2 is included inside of the Mandelbrot set. As you can see, numbers inside the Mandelbrot set stay bounded. Those outside shoot off towards infinity. But how can we prove that the main part of the Mandelbrot set is a cardioid? We can start by analyzing the attractors of the Mandelbrot set, where the points tend to converge. This will occur whenever the absolute value of the derivative of our equation, z squared plus c, is less than 1. Let me clarify. In this respect, the absolute value has more to do with the complex number's distance from 0, its modulus, than its sign. And we know that the derivative, or rate of change of our equation, must be less than 1 for it to be shrinking rather than growing. Taking the derivative of our equation, we are able to simplify it, eventually getting the absolute value of z is less than 1/2. And, as you can see, whenever I input a point somewhere inside of the main cardioid, it always attempts to converge inside of this radius 0.5 circle. But we know that this isn't a complete proof yet. Perhaps there's a better and more elegant way to write our equation. A circle in the complex plane can be represented by e to the I theta, so we can represent our boundary equation by writing 1/2 e to the I theta. Now, we have to ask the question, for what values of c will z be contained in the boundary? Isolate c from our original equation, z squared plus c, by subtracting z squared from both sides. C is equal to z minus z squared. If the boundary of z is equal to 1/2 e to the I theta, and c is equal to z minus z squared, then we can substitute in for z, simplify, and finally, we are left with 1/2 e to the I theta minus 1/4 e to the 2 I theta. And if we graph it, we see exactly the cardioid of the Mandelbrot set. But what happens if we change our original equation slightly? Instead of starting out with z squared plus c, what would happen if we started out with a different exponent? This creates the Multibrot set, described by the equation z to the n plus c. In this particular animation, n starts at 0 and goes to 6. And this animation should seem familiar. The main part of each fractal is an epicycloid. Can we generalize the proof that we found before to work for any exponent n? Perhaps this could shed some light on why these epicycloids are appearing in the Multibrot set. We already know that the boundary of all attracting fixed points can be described by the derivative of z to the n plus c. After taking the derivative and then simplifying, we are left with the absolute value of z being equal to 1 over the n minus 1 root of n. Like our last proof, this generates a circle in the complex plane. After we isolate c and resubstitute this back into our equation, we can simplify and also write it using fractional and negative exponents to make it look neater. And this is what we are left with. N to the negative 1 over n minus 1 times e to the I theta minus n to the negative n over n minus 1 times e to the n I theta. Even though this is in a quite different form, we can draw some parallels to our parametric representation of an epicycloid. Both of our equations are being divided by one less than their variable. And each equation has two main terms. In one, the input is being multiplied by the variable, and in the other, the whole term is. And if we test our equation at n equals 3, we do see the exact same nephroid, and at n equals 4, the trefoiloid. But this brings about another question. If we use a negative exponent, will we see a hypocycloid? And if so, can we use our equation to predict it? Setting n equal to negative 2, we do see the tricorn shape. And there is a sibling of the Mandelbrot set, known as the Mandelbrot Set, or sometimes the Negative Mandelbrot Set. I think it's pretty fascinating that we're able to use this generalized equation and our knowledge of epicycloids to make predictions about this fractal. Sometimes, making connections is more important than finding answers. And we could have made more of them. In math, it's fascinating how something so seemingly simple can lead to something so complex.